impulse and momentum problems. So a force is required to change momentum. You could increase the momentum, decrease it, or change it, which really means you're changing the velocity. So I enjoy looking at these pictures because you can see how the golf ball is flattened. Quite a bit of controversy behind these pictures as I tried to find one that bit cropped up. Here's another picture and one more. Changing the momentum of a large ship, it's going to take a long time to be able to bring it to a stop. It's going to take a long time to bring a train to a stop as well. So remember, impulse is force times time, and that is equal to your change in momentum. So if we're just solving for impulse, we can use the variable j, or we can set F times t equal to m times v. So our first example, we have a tennis ball that leaves the racket on a serve with a speed of 55 meters per second. The mass of the ball is 60 grams, and it's in contact with the racket for 4 milliseconds. Determine the average force on the ball. So let's list what we know. We have a speed, so that's going to be its velocity of 55 meters per second. Now, is that VI, is that VF? Because our basic equation is Ft equals m delta v. Now, a lot of times you'll see F delta t equals m delta v. So if we say that's its final velocity, let's say its initial velocity is 0. The mass of the ball, 60 grams. I've encouraged you to use kilograms, and you need to when you're using a force. So divide by 1,000, you get 0.6 kilograms. It's in contact with the racket for 4 milliseconds. So our delta t is 4 milliseconds, or 4 times 10 to the minus 3 seconds. We're solving for average force. So, looking at our basic equation, F delta t equals m delta v. Solving for F, we get mass times your change in velocity divided by your change in time. Our mass is 0.06 kilograms. Our change in velocity, it's 55 meters per second minus 0. And our change in time is 4 times 10 to the minus 3 seconds. Make sure you change the milliseconds to regular seconds. Notice your units, nothing cancels. So your units end up being kilograms, meters per second squared, which is the same thing as a Newton. If you do your mathematics, you get 825 newtons as your force. Our second example has you washing a car, and the water's leaving the hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second. And it's aimed at the side of the car, which stops it. So your VI is 20. Your VF for the water is 0. We want to know the force exerted by the water on the car. So again, we want to solve for F. Now notice we don't have a time, but we have a rate at which the water leaves the car. So we know our basic equation is F delta t equals m delta v, and we're solving for our force. So if we think about mass, we could say mass is 1.5 kilograms per second, and if we assume our time period is 1 second, we can say 1.5 kilograms is our mass if our delta t is equal to 1 second. So that's how you take care of those units. Our VF is 0, our VI is 20 meters per second, and we're trying to find our force. So once again, I'm going to write my equation. Rearrange, you have F equals change in momentum divided by your change in time. Your mass, the water was 1.5 kilograms in a second, times it came to a stop when it hit the car, and it started at 20 meters per second, divided by the time period was 1 second. So the 1 doesn't change anything numerically, but if you multiply things out, you get a nice force of 30. It's actually negative 30 newtons. Remember, our units are kilograms times meters over seconds squared. So we have a force in newtons.